Hello, space fans, and welcome to another edition of Space Fan News. In this episode, astronomers are finally starting to get direct images of planets around other stars. And not only that, for the first time, ground-based telescopes are actually getting measurements of the atmospheres of these galactic neighbors. Now, whenever we talk about exoplanets here on SFN or on one of our many hangouts that we have on new exoplanet discoveries, we always hear about looking at these planets via indirect methods, like the transit method, which measures tiny dips in brightness of a star when a planet passes between us and the star. And there's also the radial velocity method, where you look at a star's light through a spectrograph, and then you watch the spectral lines go back and forth as the planet tugs on the star in its orbit. There's also weak gravitational lensing, which causes a characteristic blip in the star's light as the planet passes in front and bends that light through its gravitational field. All of these are indirect ways of seeing an exoplanet, though. They aren't direct pictures of the planets themselves. Now, as you can imagine, these kinds of images are hard to take. The star is so much brighter than the planet itself that it completely blinds us when we try to see it. So, the holy grail of exoplanet studies is the direct imaging of these planets. When we can do that, then we can really study the details about the planet and learn really key things like whether it has an atmosphere or if there's any biosignatures of life that we can tease out of the light signal coming from that planet. So now, believe it or not, we do have some direct images of exoplanets, and in fact, we have some images of a system of exoplanets. This is HR 8799, which is 129 light years away in the constellation of Pegasus and is about 1.5 times the size of our Sun. 3 planets here, roughly 10, 10, and 7 times the mass of Jupiter, orbit the star. The sizes of the planets decrease with the distance from the parent star in this case, much like the giant planets do in our system. And folks, this was taken in 2008. Wow. Now, there have been other direct images of exoplanets, but this is the only multi-planet system that we have images for. And for a long time, this was the picture of the solar system, right here. 3 planets, B, C, and D, with D being the smallest, at 7 times the mass of Jupiter. The other 2 were 10 times the mass of Jupiter. Then, in 2010, Keck found a 4th planet, HR 8799e. And it took a while, I guess, because it was really close to the star. It's the smallest of the bunch, with about 7 times the mass of Jupiter, and it orbits the star every 200 years. Now, the other planets are pretty far away from the star. They're 24, 37, and 67 AU from the host star. The furthest planet in the new system orbits just inside a disk of dusty debris, which is similar to that produced by the comets of the Kuiper Belt in our solar system. And just for reference, Neptune is about 30 AU, so the closest of these are about as far away as Neptune is. Now, here are 7 years worth of observations showing the system. HR 8799e is the closest, and from the way the people at Keck describe this, it looks like adaptive optics were used to steady the atmosphere, and then a subtraction was made to get rid of the main star. Remember, these planets are huge, way bigger than Jupiter, which is one reason I think we can see them so well. So the host star is a bright blue A-type star, and it's also very young, with less than 100 million years old, which means its planets are still glowing with heat from their formation, which also helps us to see them a little bit better. But the story's not over. Late last month, astronomers from ESO's gravity instrument managed to get some details about the innermost planet, HR 8977e, by using VLT's 4-unit telescopes to work together to make a single, larger telescope using a technique known as interferometry. This creates a super telescope, the VLTI, and it collects all the light and it precisely disentangles the different light from both the atmosphere of HR 8799e and the light from its parent star. Now, if this sounds familiar, this same technique was used by radio telescopes all over the world to create an Earth-sized telescope, the Event Horizon Telescope, that had enough resolution to see the black hole at the center of M87 directly. Well, by using VLT's 4-unit telescopes in a really complicated way, here's the graphic, they were able to measure some of the details of the atmosphere of HR 8799e. And, as usual, there were surprises. First, they found way more carbon monoxide than methane, which is something you weren't expecting, and because that usually doesn't happen. The CO usually equilibrates into methane, and that didn't appear to happen here. They think maybe that there are high vertical winds within the atmosphere preventing the carbon monoxide from reacting with the hydrogen to form methane. Now, this place also isn't all that hospitable. Temperatures are around 1,000 degrees Celsius, so again, we won't be moving there anytime soon. But the big news here is that this work can be done from the ground using interferometry and adaptive optics. Now, if you want to learn more about the VLT unit telescopes, we did a hangout on this a few weeks ago talking about the science and the equipment at ESO, so please check that out. I'll put a thing up here. Okay, well, that's it for this episode, space fans. Thanks to OPT for sponsoring SFN. If you need a scope, please check them out, folks, because they're helping produce SFN and helping me do videos. And if you go there, please, tell them I sent you. SFN is also made possible by all of Deep Astronomy's Patreon patrons, whose kind generosity make all videos possible. So thanks to all of you. And thank you for watching. And as always,